Mathew Kavalekalam's Ph.D. defense here today. My name is Jesper Kjær Nielsen, and I'll be the moderator for this Ph.D. defense here. So on behalf of the technical faculty of IT and design at Aalborg University, I would like to welcome all to this Ph.D. defense here today. Mathew has submitted his thesis as a part of the requirement for the Ph.D. degree. The supervisors for his dissertation were Professor Mads Græsbøll Christensen and Research Manager Jesper Boldt from Research. The thesis is entitled Model-Based Speech Enhancement for Hearing Aids, and Mathew's thesis is based on a number of scientific papers with an introduction. The Dean has appointed an assessment committee to evaluate the work of Mathew. There are two external members and one representative from Aalborg University, who is also the chairman of this committee. It is really a pleasure that two international recognized scientists have accepted to be part of this committee. And on behalf of the faculty, I'd like to welcome, so first of all, Professor Rainer Martin. Rainer Martin received a master's degree from Georgia Institute of Technology in 1989, and later his PhD degree from RWTH Aachen University in 96. From 96 to 2002, he was a senior research engineer with the Institute of Communication Systems and Data Processing at RWTH Aachen University. From 98 to 99, he was a technology consultant at the AT&T Speech and Image Processing Services Research Lab in New Jersey. And from 2002 until 2003, he was professor of digital signal processing at the Technische Universität Braunschweig. And since 2003, he has been a chair professor of information technology and communication acoustics at Ruhr-Universität Bochum, where he also served as the Dean of Electrical Engineering and Information Sciences Department. His research interests are signal processing for voice communication systems, hearing aid instruments, and human-machine interfaces. He's the co-author of the book Digital Speech Transmission, Enhancement Coding and Error Concealment, and the co-editor of the book Advances in Digital Speech Transmission. Rainer has served as an associate editor for the IEEE Transactions on Audio, Speech and Language Processing, and is an associate member of the Audio and Acoustic Signal Processing Technical Committee. He's a fellow of the IEEE, and among other projects, Rainer has been sub-project leader in the European Integrated Project, Hearing and Communication in the Communication Society, and the coordinator of two European Marie Curie initial training networks. Then in the committee, we also have senior research scientist Emmanuel Vincent. Emmanuel Vincent is a senior research scientist with Inria Nancy in France. He received the PhD degree in music signal processing from the, now I'll try in French, Institut de Research et Kommunikationsakustik Musique. Is it okay? Yeah. At the IRCAM in Paris in 2004, and he worked as a research assistant with the Center for Digital Music at Queen Mary, University of London from 2004 to 2006. His research focuses on statistical machine learning for speech and audio signal processing, with application to audio source localization and separation, speech enhancement, and robust speech and speaker recognition. He is a founder of the series of signal separation evaluation campaigns and the Chime Speech Separation and Recognition Challenges. Emmanuel has served as an associate editor for the IEEE Transactions on Audio, Speech and Language Processing, and is associated member of the Audio and Acoustic Signal Processing Technical Committee. Among other projects, he is the coordinator of the Horizon 2020 comprised project. Then in the committee, we have also as chairman of the committee, Thomas Arildsen, who is associate professor with the Department of Electronic Systems here at Aalborg University. And for those of you who do not know Thomas, then he has been with Aalborg University since 2006 and is now focused on the topics of scientific computing and signal processing. So on behalf of the faculty, I would like to acknowledge the big effort done by the committee in evaluating this thesis. The program for today is divided into two sessions. So first, the Ph.D. Candidate will give his Ph.D. lecture for a maximum of 45 minutes. And then we will have a short break before the committee will raise questions and comments to the Ph.D. candidate. When the committee has no further questions, then the audience will also have a chance to ask questions or give comments on my directions. So if you have any questions to the Ph.D. candidate, then please approach me during the break. This session here will end no later than 4 o'clock, and after that there will be a reception where you are of course all very much welcome, and it will take place in Create's common room. So with that, I would like to give the floor to you, Mathew.
Good afternoon, everyone. My name is Mathew, and I'm a PhD student at the Audio Analysis Lab at Aalborg University. And today I'm here to defend my PhD thesis. So I would like to thank the committee and all of you present here. So the title of my thesis is Model-Based Speech Enhancement for Hearing Aids. So first I would like to give a short motivation for my work. So imagine a situation like this as shown in the picture, where many people are talking at the same time with each other. So in such situations, humans with normal hearing have the remarkable ability to focus his or her attention to a particular speaker of interest. However, for people with hearing loss, it's quite difficult in such scenarios. So here I'll give you a short example of how the speech would sound like in such a scenario. So first I'll play back the clean speech that you're interested in, and after that I'll play back the noisy signal.
The dividend is payable June 1st to stock of record May 7th. The dividend is payable June 1st to stock of record May 7th.
Yeah. So as you can hear, this noise present in the background can lead to severe degradation in speech intelligibility for people with hearing loss. So in such situations, hearing impaired people often rely on a hearing aid to have a better experience, and hearing aids performs tasks such as dynamic range compression, feedback cancellation, speech enhancement, etc. However, unfortunately, the performance of the current hearing aid technology in such situations has been observed to be limited. So the main focus of this thesis has been to develop speech enhancement algorithms capable of enhancing the user experience in such adverse scenarios. So these are the papers that I have published during this project, and during this talk I will cover the first 7 papers in this list. Yeah. So moving into the contents, first I will introduce the basic signal model that has been used in this thesis, and after that I will talk about single channel speech enhancement, where I will first talk about noise power spectral density estimation, which is a critical component in many of the speech enhancement systems. And after that, I will introduce you to a single channel speech enhancement method based on non-negative matrix factorization. And then we will move on to the case of binaural speech enhancement, where I explain the binaural estimation of filter parameters and filtering of the noisy signals. And after that, I will talk about 2 hearing aid applications. And finally, I will give a brief summary of my contributions and conclude. So moving into the signal model, the noisy speech set is modeled as a sum of clean speech and noise. And inspired by the human speech production mechanism, the clean speech is here modeled as a combination of an excitation signal and the vocal tract. So here U of n is the excitation signal, which is basically the signal coming out of the vocal cords. And the vocal tract is modeled as an all-pole filter. So using these assumptions, the clean speech can be modeled as an AI process, where AI are the AR coefficients and U is the excitation signal. So now if we assume stationarity, a frame of clean speech can be modeled as a multivariate Gaussian distribution as shown there, where sigma U square is the excitation variance and RS is the gain normalized covariance matrix. And this gain normalized covariance matrix can be asymptotically approximated as a circular matrix and which can be then diagonalized by the Fourier transform. So here F is the DFT matrix and D is DS is a diagonal matrix defined as shown there, which basically has the power spectral density corresponding to the AR coefficients along its diagonal. And similar to the speech, a frame of noise is also defined as follows, where sigma V square is the excitation variance and RW is the gain normalized covariance matrix. So this is the basic signal model that we have used in this thesis, and majority of the work done in this thesis is built up upon this model. So now we'll move into single channel speech enhancement, where I'll first talk about noise power spectral density estimation. So noise power spectral density estimation forms a critical component in many of the speech enhancement system. And here we have a basic block diagram of the speech enhancement system where we perform noise reduction based on the estimated noise Ph.D. And these are some of the popular noise Ph.D. estimation algorithms existing in literature. And most of these rely on some sort of statistical differences between the speech and the noise signal. So given a frame of noisy signal, we need to estimate the noise Ph.D., which can be defined as shown there. And this conditional expectation can be rewritten in terms of the posterior density P of W given Z as follows. So by looking at this equation, we can see that the problem of noise Ph.D. estimation is essentially that of computing the second order moment of this posterior density P of W given Z. So to compute this posterior, we here bring forth k statistical models, which can be incorporated into the previous equation as shown there. So we now have a model averaged noise Ph.D. estimator where the posterior model probabilities ensure that the models that explain the data well contribute to the larger data. And in this work, we have used AR models to model both speech and noise, where AK and VK are the AR coefficients for speech and noise, which are picked from a trained speech and noise codebook, and which has been trained already. So a particular model here refers to a particular combination of the speech and noise codebook entries. And the excitation variances are treated as unknown random variables with the following prior. So to compute the noise Ph.D. estimate, here we have to estimate the model, the posterior model probabilities and the second order moment of this posterior density. And to do this, we here use a variation framework to produce an analytical approximation if we assume that the full joint posterior factorizes as shown there. And after the derivation, we see that this factor is given by a multivariate normal distribution with the mean and covariance metrics as shown there, and the second order moment of this posterior density can be obtained by that equation, which is then substituted back into the previous equation to get the final noise Ph.D. estimate. So moving into the experiments, the first experiment here evaluates the tracking speed of the proposed method in comparison to a few other methods. And to do this, we have here used the modulated wide Gaussian noise, whose noise variance varies with a frequency of 2 Hz. And it can be seen that the proposed method given by the red color performs better than the other methods. And on the right here, we have a Babel noise spectrogram for 0 dB, and below we have the estimated spectrogram from the proposed method and one for the MMSE tracker. And it can be seen that the proposed method better resembles the actual noise than the MMSE tracker, and at the same time it is also able to capture the non-stationarities present in the noise, which is actually smoothed out by the MMSE tracker. And now we use a few objective measures to evaluate the performance. The first one is the log spectral distortion, which is divided into over and underestimation errors. And the three other measures are related to the enhancement performance. So in this, we are using the noise Ph.D. estimate. We here perform speech enhancement using a Wiener filter where the a priori SNR is estimated using a decision-directed approach. And it can be seen that the proposed method outperforms the other method in terms of the log estimation error, segmental SNR, and the segmental noise reduction. However, in the case of segmental speech SNR, which is related to the speech distortion, the proposed method performs worse than the other methods. So now we move on to a single channel speech enhancement method, which is based on non-negative matrix factorization. So I mentioned previously that we used a Wiener filter for speech enhancement, and this can be written in the frequency domain as shown there, where phi SS is the PSE of the clean speech and phi WW is the PSE of the noise signal. And this can be rewritten in terms of the a priori SNR as shown there. And previously, the a priori SNR was estimated using a decision-directed approach. However, we now explain how we can compute the a priori SNR by jointly estimating the speech and noise PST using a supervised NMF-based approach. So, NMF is a very popular technique to approximate non-negative data, and it has been applied in different fields. So, in case of speech signals, they can be used to model the power spectrum or the magnitude spectrum, which are non-negative in nature. And NMF techniques basically models the observation as a linear combination of spectral basis vectors, with each basis vector having a time-varying gain, which is also called as the activation coefficients. So in this figure, we have an example of NMF being performed on a 12-second piano signal into two spectral basis vectors and the corresponding activation coefficients. And from this figure, we can see that the second spectral basis vector is active in the first segment, the first basis vector in the second segment, and both the spectral basis vectors are active during the third segment. So in conventional NMF-based approaches, the spectral basis vectors are not parameterized by any, are not constrained by any parameters other than that they have to be non-negative. So in this work, we investigate the effects of parameterizing the spectral basis vectors using AR coefficients, and this has similarities to the model in this paper where it was used for decomposing the spectrogram of clean speech. However, the way of modeling the way of estimating the model parameters are quite different. So in this work, we investigate how this parameterization helps for speech enhancement. So moving into the signal model, a frame of noisy signal in the time domain is modeled as a sum of U AR process, where the first US AR process correspond to the speech and the remaining correspond to the noise. And each of these AR processes can be expressed as a multivariate Gaussian with the properties that we have already introduced before. And so the likelihood of the observed data as a function of the spectral basis matrix and the activation coefficients can be written as shown there. And since we are considering supervised enhancement, we assume that the spectral basis matrix D is already trained a priori. So our objective here is to basically estimate the activation coefficients given the noisy data and the spectral basis matrix D. So this here is done by maximizing the likelihood as shown here. And if we then work out the equations, we can see that the maximum likelihood estimation of the activation coefficient corresponds to minimizing the IF divergence between the noisy periodogram and the D sigma. So to obtain the spectral basis matrix, we first train a speech and noise codebook in the LSF domain, and these are subsequently converted into the AR coefficients. And the spectral basis vector corresponding to one entry in the codebook is computed using that equation. So here we have a few examples of a spectral basis vectors for the speech in blue and for the noise in red. So to use this model for enhancement, as explained earlier, our first task is to estimate the activation coefficients for the speech and noise, and this is done by minimizing the IS divergence as shown there. And this is then solved using the multiplicative update rule, and once it has converged, the estimated activation coefficients for the speech and noise can be used along with the spectral basis matrix D to get the noise speech and noise DST, which is then used to compute the Wiener filter. So moving into the experiments, the proposed enhancement framework has been evaluated for different types of noise, and we denote the proposed method as par NMF, and this has been compared to the case where we do not constrain the spectral basis vectors, and also to one other method which is an unsupervised single channel speech enhancement method. And moving to the results, here we have used the objective measure called STOI for the evaluation. So STOI is an objective measure for measuring the intelligibility of the signal, and it gives us a value between 0 and 1. So the higher the score is, the more intelligible the signal is. And in this case, the speech codebook was trained using the speaker of interest, and the noise codebook was trained using the noise of interest. And it can be seen that the parametric NMF outperforms the non-parametric counterpart and the other single channel speech enhancement method. And these are the results when we use general speech codebook and general noise codebook. So compared to the previous slide, it can be seen that the results degrade slightly, but the parametric method still outperforms the non-parametric case even here. Yeah. So next we'll move into binaural speech enhancement. So it is often the case that the hearing impaired is fitted with hearing aids at both the ears. So in this case, we receive two noisy signals, one for the left and one for the right. So one way to perform enhancement in that case would be to do single channel speech enhancement for both the channels independently as shown in the left figure. And this setup is called as the bilateral setup. But one disadvantage of this setup is that it may not preserve the binaural cues, which actually plays a major role in source localization. So in state-of-the-art hearing aids, it is possible to wirelessly communicate information from one ear to the other. So this technology can be exploited to jointly estimate the filter parameters using the information in both the left and the right ears. And this can be done for the cases of multiple microphones per ear or single microphone per ear. But in this thesis, we will restrict ourselves to the case of single microphone per ear. And all these above mentioned algorithms, they perform enhancement in the frequency domain and do not take into account any speech production model. So we try to do this here. And moving into the signal model, we here assume that the speaker of interest is in the nose direction of the listener, and this leads to the clean speech at the left and the right ears being modeled by the same AR coefficients and excitation signal properties. And for the excitation signal, we have considered two cases. In the first case, we modeled it as a white Gaussian noise, as we have done previously, and this is denoted as the unvoiced model. And the second case, inspired by the work done in that paper, we modeled it as shown there. So here P is the pitch period, and V of P is the degree of voicing, and D of N is a white Gaussian noise. So this model was shown to better represent the excitation signal, as it can take into account both the voiced and unvoiced speech. And similar to the speech, The noise component at the two ears are also represented as an AR process having the same parameters across the channels. So based on the introduced signal model, the parameters that have to be estimated here are the AR coefficients and the excitation variances of speech and noise, and the pitch parameters corresponding to the clean speech. So this is a basic block diagram of the proposed enhancement framework, where we use a fixed lag Kalman smoother on both the channels to perform speech enhancement. So we use the fixed lag Kalman smoother as it can take into account the speech production model that we introduced earlier. And the excitation signal for the voiced, unvoiced model can be easily integrated into this framework. However, in case of using the unvoiced model, in principle, we can also use a frequency domain Wiener filter on both the channels. So the STP parameters are here estimated using a codebook-based approach, and the pitch parameters for the clean speech are estimated using a method based on the harmonic model of speech. So using a fixed lag Kalman smoother from a speech enhancement perspective requires the speech and noise AR signal model to be written in the state space form as shown there. So here S and W are the state vectors for the speech and noise, and A and C are the state evolution matrices for the clean speech and noise. And the observation equation can be written as follows. And in the case of voiced unvoiced model, for the state space equation, we have an extra state vector which corresponds to the excitation signal. And the observation equation looks like that. And once we have the state space equation and the observation equation, we can formulate the prediction and the correction stages of Kalman smoother to obtain the enhanced signal. So given a frame of binaural noisy signal, the MMSE estimate of the filter parameters can be written as shown there. And if we then assume that the PDF of the AR coefficients for speech and noise can be modeled using the codebook entries, then we can rewrite the above equation as shown there. So to compute this expression, we need to first compute the maximum likelihood estimates of the speech and noise excitation variances for a particular combination of the codebook entries. And this is done by maximizing the likelihood, and which can be shown to be equivalent to minimizing the sum of these IS divergence terms. So here PZL is the noisy periodogram at the left ear, and PZR is the noisy periodogram at the right ear, and P hat of Z is the model noisy spectrum using the codebook entries. And once the excitation variances are computed, we can compute the likelihood, which is then substituted back into this equation to get the final estimate of the filter parameters. So moving into the experiments, we have used both subjective as well as objective measures to evaluate. And the proposed method can be categorized based on whether it is a binaural or bilateral, or on the basis of the excitation signal model, or on the basis of the type of the codebook. And the different configurations are named as shown in the tables. And then we have used few reference methods for the binaural and the bilateral case as shown there. And in this slide, we have the STOI and PEST measures which are averaged across channels. And on top we have the bilateral methods, and below we have the binaural methods. And it can be seen that the binaural methods perform better than the bilateral methods. And also we get the best performance in the case where we use the binaural and the voiced unvoiced model for the excitation signal. And it can also be seen that using a speaker-specific codebook gives an improvement which is expected. Yeah. So as you have seen before, the usage of the voiced unvoiced model gives an improvement in the performance, but it also comes at a higher computational cost. So in this work done by Go, the sparsity of the matrices involved were exploited to reduce the number of computations by a factor of 900. And in the case of the estimation of STP parameters, the computations are related to the number of model combinations, which is given by NS times NW. So here NS is the number of speech codebook entries and NW is the number of noise codebook entries. So we had investigated the usage of a dual channel noise Ph.D. estimate alone in combination with the speech codebook. So in this case, we do not have a noise codebook. And even though this led to slight degradation in the performance, it reduces the number of models to NS. And for each model, then we have to estimate the excitation variance iteratively. And this takes around 10 iterations to converge. And for the subjective listening test, we have evaluated one of the proposed algorithms. And we have used Mushra as well as intelligibility tests. And if you look at the Mushra scores, you can see that the proposed method performs significantly better than the noisy signal and reference method. And for the intelligibility test, we get an improvement of up to 15 percentage points at -8 dB SNR. So now I'll play back a few audio demos. So first I'll play back the noisy signal, and after that the enhanced signal by the reference method, followed by the enhanced signal by the proposed method.
Play green with G0 now. Play green with G0 now. Play green with G0 now.
So in the previous case for binaural speech enhancement, we assumed that the speaker of interest is in the nose direction of the listener. So hence the AR coefficients and the excitation variances were assumed to be identical across the channels. But this assumption may not always hold true. So here the position of the speaker was set to 40 degrees right of the listener. And the first figure here shows the excitation variance for the left and the right channel. And it can be seen that because of the head shadowing effect, there is a clear level differences between the left and the right channels. So motivated by this observation, we here model the speech excitation variance across the channels using a scale term C. And this scale term is then estimated using the multiplicative update rule as shown here. So when we take into account the scale term, we can see that the proposed algorithm is can take into account the level differences between the left and the right channel as shown in the figure on the top. And this modification also leads to improvements in the spectral modeling. So here we have, in the table, we have the IS divergence between the noisy periodogram and the modeled spectrum. And you can see that the proposed method gives better scores than if we assume identical parameters across channels. And even in the case of enhancement, when the speaker was set to -50 degrees left of the listener, you can see that the proposed method gives an improvement, especially in the lower SNR region. Yeah. Now we will discuss about some potential hearing aid application. So the first application that we are going to discuss here is a hearing aid controlled beamformer, where we discuss how we can use an external device along with the hearing aid. And the external device in this case is a circle array which can be used to focus on the signal coming from a particular direction. So to make it more clear, consider this situation where the hearing aid user is sitting at a dinner table or is at a meeting with colleagues. And from the figure, we can see that the hearing aid user is interested in listening to speaker A. So from the perspective of the hearing aid user, speakers B and C are interferers. So our objective here is to focus the beam pattern of this external device towards speaker A. So to do this, we need to estimate theta s, and this requires some sort of communication between the external device and the hearing aid. So to compute the data that is to be transmitted, conventional beamformer focusing on the nose direction of the listener is done to get a preliminary enhanced signal, which is denoted as XHA of N. And at the same time, the external device focuses its beam on towards I different candidate direction, which are uniformly spaced in the azimuthal plane. So now we have a total of I plus 1 signals, and our objective here is to estimate theta s using this set of signals. Yeah. So how we do this is we first use the model that we introduced for the case of parametric NMF to model the signals at the hearing aid as well as the circular array for different candidate directions. And using this model, the PSP of the model signal at the hearing aid can be shown to be d sigma h of A, where d is the spectral basis matrix and sigma HA is the activation coefficients. And in case we observe more than one frame, these sigmas can be arranged as the columns of matrix to get the capital sigma of HA. And similarly, the PSP of the model signal at the circular array can be written as follows. So once we have estimated the set of activation coefficients for the signals, we have used two methods to estimate the direction. The first one is to choose the direction that minimizes the IS divergence between the model spectrum at the hearing aid and the model spectrum at the circular array for the I candidate directions. And the second way is by choosing the direction that maximizes the correlation between the activation coefficients at the hearing aid and at the circular array for the I candidate directions. So it can be seen that in both the methods, the only information that we have to transmit is the activation coefficients from the hearing aid to the external device. And this is generally much better than the raw signal that has to be transmitted. So moving into the experiments, so this is the simulation setup that we have used. So the speaker of interest in this case is denoted by the green dot, and the red dot are the interferers, and the circular array is shown in the center, and the hearing aid user is shown on the top. So this figure here shows the beam pattern of the circular array for the I candidate direction. And in our case, I was chosen to be 8, and these are the beam patterns for the different for the 8 candidate directions. So looking at the results, the two figures on the top show the accuracy in choosing the right candidate direction for the two methods as a function of the SNR and the memory. So the memory here is related to the number of frames that is used for the comparison. And it can be seen that the correlation-based method clearly performs better than the IS-based method. And next we use this framework for speech enhancement using a binaural Wiener filter, which requires the knowledge of the statistics of the clean speech or noise. And in this work, the clean speech statistics used in the functioning of the Wiener filter is estimated using the beamform signal from the candidate direction. So in this figure, the green and the red curve denotes the scores for the beamform signal at the circular array and the candidate and the hearing aid, and the violet and the green curve correspond to the case where we use these signals for binaural speech enhancement, and the scores are again averaged across the left and the right channels. So now I'll play a few audio demos. So the first signal what I'll play is the clean speech, that is that's the speech that we want to hear. And next I'll play the unprocessed, where we do not do any enhancement, and after that I'll play the enhanced signal using the proposed binaural speech enhancement method.
The parent company added that it may seek other business opportunities subject to the availability of
Regional banks.
The parent company added that it may seek other business opportunities subject to the availability of. The parent company added that it may seek other business opportunities subject to the availability of.
So it can be seen that the proposed method gives an improvement over the unprocessed signal in terms of removing the interference. Yeah. So the next application that we will discuss here is that of non-intrusive speech intelligibility prediction. So it is in some cases desirable to predict the intelligibility of the desired of the degraded signal objectively for the online optimization of the hearing aids. So one way to do that is by using STOI, which is an objective measure that I have already explained. And it's quite well established method for measuring the intelligibility. So how STOI works is that it takes the time frequency representation of the clean speech and the degraded speech, and it then group into short time temporal segments, and then a correlation coefficient is then measured between them to get a STOI score between 0 and 1. But one problem that we have here is that STOI actually requires the clean speech signal, so it is actually an intrusive measure. But in case of hearing aids, we have access to just the degraded speech. So what we propose to do here is that we propose to estimate the clean speech and noise statistics using a codebook-based approach, and this is then used to construct the clean and degraded spectrum, which is then fed as an input to the next steps in STOI. So moving into the results, here we have plotted the estimated scores using the proposed method against the STOI score for different SNRs. And on the right we have the average of this, and it can be seen that there's a very good correlation between the scores obtained using the proposed method and the scores obtained using the using the intrusive STOI measure. And below we have used the subjective test to validate this. So the blue curve is the results obtained using the subjective test, and the yellow is the one obtained using the proposed method. And there also you can see a very good correlation between the two curves. Yeah. So finally, we now have a summary of the contributions. So the works that I have discussed so far can be categorized into single channel and binaural methods, and all of them use trained spectral models of speech and noise. So first I talked about a noise PST estimation algorithm, which was found to outperform the state-of-the-art methods in terms of estimation accuracy and speech enhancement performance. And after that, I talked about a single channel speech enhancement method based on parametric NMF, where we investigated the effects of parameterizing the spectral basis vectors using AR coefficients. And this was found to show improvements over the case of NMF with unconstrained spectra. And after that, I talked about binaural enhancement of speech, where I explained the binaural estimation of filter parameters. And we showed using objective measures as well as subjective measures the benefit of using the proposed method. And then I talked about two applications of these methods. And the first one, I talked about the speech intelligibility prediction using a non-intrusive method, and this was found to correlate well with the intrusive STOI measures. And one other application that I talked about was how to use an external device such as a microphone array along with the hearing aid, and this was found to be robust to reverberation as well as noise, and also gave an improvement by using it for binaural speech enhancement. And moving into the conclusion, so in this thesis we have proposed methods for different applications like noise BST estimation, speech enhancement, intelligibility prediction, collaboration with an external device, etc., based on a speech production model. And the proposed methods were able to show benefits in terms of objective measures as well as subjective measures, where we showed improvement in intelligibility as well as quality. And Another class of algorithms that has gained attention in the recent years are the deep neural network-based methods. So one interesting future work would be to identify the pros and cons of our method in comparison to the DNN-based methods. For example, on the basis of the amount of training data that's required, the latency or the memory that's involved, or generalizability to unseen conditions, the computational complexity, and the performance. And since the parameters that we have used, that we have trained in our algorithms are the AR coefficients of speech and noise, which are low dimensional in nature, I think that the online training of speech and noise models needs to be investigated. And we think that the collaborations and external device can be very helpful in this regard to provide us with the training data that's required for training these models online. And now for a few acknowledgements, I would like to thank my supervisor and my co-supervisors, so Mads, Jesper Boldt and Jesper Nielsen, for their help during this project. And also thanks goes to my colleagues at the Audio Analysis Lab and all the other colleagues at Create, and to my friends in Aalborg and India, to my family, my parents, grandparents and my brother, and last to my lovely wife Maya and my son Abraham, who just turned 2 months old yesterday. Thanks for the attention.
Thanks, Matthew. So there will be a break now, and just outside the door here, there's some coffee and chocolate